You ever been in that spot where you have to design a network, but all you're given is how many devices need to connect? Yeah, it's a classic problem. Well, today, we're going to solve it by taking the usual process and flipping it completely upside down.
Okay, so picture this. You're handed a big block of IP addresses. Your boss doesn't just say, "Hey, I need 4 new networks." Nope. Instead, they say, "I need networks, and each one has to support at least 40 different devices. Laptops, phones, you name it." So, where do you even begin? That's the puzzle we're going to crack today.
And to make this really stick, I need you to play a role. Put on your network admin hat. I'm opening up a chain of coffee shops, and you're the expert I've called in to build the network. Let's do this.
Okay, here's the job. Our starting point is a simple 10.1.1.0/24 network. Your goal is to chop that up into 3 separate networks, one for each coffee shop. But here's the kicker, the really important part. Each one of those networks must have room for at least 40 devices. Think cash registers, Wi-Fi for customers, the whole deal.
This is exactly where we have to totally flip our thinking. Normally, we start by thinking about how many networks we need, but not today. Today, we start by thinking about how many hosts or devices we need, and that's why I call this the upside-down method.
Yeah, this table lays it out perfectly. The old way, you're looking at the subnet mask from the left, and you borrow bits to create more networks. With our new method, we do the exact opposite. We start from the far right of the mask, and we save the bits that we absolutely need for our hosts first. It's a complete 180 from the usual process.
Now, I know this might sound a little weird, but trust me, it's not as complex as it seems. I'm going to walk you through a really simple 4-step process that gets you the right answer every single time. Let's break it down.
So here's our game plan. First, we find our block size. That's just how big each network needs to be. Second, we save the bits for our hosts. Third, we find our increment, which tells us where each network starts. And finally, we just map out the networks. All right, let's dive into step 1.
So first things first, we leave a block size big enough to handle our 40 devices. Think of it like picking the right size box. And to do that, we're going to use a super simple chart that tells you how many hosts you get for a certain number of bits.
Okay, take a look at the chart. If we use 5 bits, we get 32 hosts. Is that enough for our 40 devices? Nope, not even close. So we have to go up to the next level. 6 bits gives us 64 hosts. That's perfect. It covers our 40 and even gives us some room to grow. So our block size is 64.
And the magic number that got us that block size of 64 was 6. 6 host bits. You got to remember that number, because those 6 bits are sacred. We cannot touch them, we have to protect them, or save them no matter what. Okay, this is the most important part, the actual upside-down move. We're going to look at our subnet mask in binary. We start from the far right side and count in 6 spots. We basically draw a line in the sand right there. Those 6 bits are now saved for our hosts. Any other leftover host bits to the left of that line? They get flipped into 1s. They're about to become network bits.
Let's see what this actually looks like. Our original /24 mask has all zeros in that last octet, right? So we count 6 bits from the right and we save them. But look, there are still 2 zeros left over to the left of our saved bits. We hack those, bam, they get flipped to 1s. They just got a promotion from host bits to network bits.
All right, on to step 3, finding our increment. This is going to be the magic number we use to count out our new networks. And the rule is super simple. You just find the place value of the rightmost bit that we just flipped to a 1. You know, in binary, the values go 128, 64, 32, and so on. Well, that last bit we flipped is sitting in the 64's place. So our increment is 64. Easy as that.
And just like that, we're on the final step. We just need to figure out our new subnet mask. We started with 24 1s in the mask, and we just added 2 more, right? So 24 plus 2 is 26. Our new subnet mask is a /26. In decimal, that's 255.255.255.192. Now we've got everything we need to build our networks. And there you have it, the final solution. The first coffee shop gets the network starting at 10.1.1.0. To find the next one, we just add our increment, 64. So the second shop starts at 10.1.1.64. Add 64 again, and the third starts at 10.1.1.128. See? Simple counting. Each of these new /26 networks gives us a block of 64 addresses. Of course, you always lose 2, one for the network ID and one for the broadcast, but that leaves us with 62 usable IPs. We needed 40, we got 62. Mission accomplished.
See, you just solved a real-world problem. Now that you've got the hang of it, let's put that new skill to the test with a little rapid-fire challenge. This time, you're not a coffee shop admin. You're working for the internet service provider.
Okay, so the phone rings. A customer needs 20 static IP addresses, and you've got this massive /16 network to pull them from. What's the most efficient subnet you can give them without wasting addresses? Go. Just think through those 4 steps we just learned.
All right, let's fly through it. Step 1, block size. They need 20 IPs. The next power of 2 up from 20 is 32. Step 2, save your host bits. For a block of 32, you need to save 5 host bits. Now we started with a /16 mask, which left us with 16 host bits to play with. We're saving 5 of them, which means 11 are left over to become network bits. Just add those 11 to the original 16, and you get 27. So our new mask is a /27. See? The system works every time.
Look, if you remember just one thing from all of this, let it be this. The big secret is just flipping how you look at the problem. Instead of borrowing bits from the left for networks, you figure out what you need for your hosts, and you save those bits from the right. That is the entire trick.
So you now have a seriously powerful skill in your back pocket. You can build a network based on how many devices it needs. But what if we made it even harder? What if I didn't give you the network address? What if all you had was a single IP, like 48.5.4.71, and the subnet mask, and I asked you to find the very first and very last address in that network? Could you reverse engineer the whole thing? Well, that's a challenge for another time.